In a previous video, we talked about how we could find the circumference and the area of circles, area being pi r squared and the circumference being 2 pi r. And we went over why this is true with a little bit of calculus. And in this video, I want to do the exact same thing, but for the sphere. And we can remember that in 3D, instead of having a circumference, you have a surface area. And instead of having an area, you have a volume. And what's the area, what's the volume of a sphere? Well, the surface area of a sphere is 4 pi r squared. The volume is 4/3 pi r cubed. Why do you divide by 3? Why do you multiply by 4? These are kind of confusing things. It doesn't make a lot of sense. It's kind of hard to remember, frankly. Well, in this video, we're going to go over why this is true. We're actually going to derive it with some calculus. And first, we're going to derive the volume. And in order to derive the volume, let's draw ourselves a sphere so we have something to work with. So we'll do the back side, front side. All right, not perfect, but it'll do. So here's our center, and let's say this sphere has some radius r. All right, so the key point is we're going to be using integration. So we need some range that we need to integrate on. And we're going for the volume, so we're going to need to find some changing value that we can integrate over that's going to give us different volumes that we can add up to get, or different areas we can add up to get the volume. And one such range, which is what we're going to use in this video, is this range from 0 to r. I'll do it a bit bigger so you can see. 0 to r. Alright, and what are we going to be adding up here? Well, it might seem natural here, in this case, that you could be adding up different disks, because at different points you're going to have different heights. At this point right here, you're going up the entire r. At a point like this, though, you might only be going up a fraction of r. At a point like this, you're going up near to nothing, and at a point like this, you're barely going up at all. So you have all these different heights, and you can draw different circles here. So we have a big circle for that one. For this one, though, you might have a little circle, and you might have a larger circle. And each of these circles here, these have area. And if we're summing up the area, I know the graph's getting a bit cluttered here, but if you sum up all the areas of all these circles, then you're going to get the volume of half the sphere. So, in more of English, the volume of half of a sphere, this is going to equal the sum, I guess we'll do it in yellow, sum from an infinite sum, so really this is going to turn into an integral, but the sum from 0 to the radius of these spheres of changing heights, circles of changing heights. So circles of different changing radii, right? And this is what the volume of half the sphere is going to be. So how can we translate this into math? Well, all right, this first part, not that bad. 1/2 v. 1/2 v is going to equal, what is the sum from 0 to the radius of circles of changing radii? Well, this sum from 0 to radius part, this is perfect for an integral. So we take the integral from 0, which is where we're starting, where we have the largest circles, to the radius, where all the way at the radius, the circles are non-existent, they're really small. And we're going to need to use, we're going to be summing up different areas of circles, so we're going to have a dx in here, and somehow, dependent on how far in the x direction we've gone, or really how far in the r direction we've gone, but that makes a little bit less sense, we're going to have the area of a circle. So we're going to have some pi times a certain radius, and I'm making it capital so we don't confuse with the constant radius of the sphere. Some, I guess you could call it dynamic or working radius for where we're at, of x squared. this is our expression. So the big problem right now is that we don't know what r of x is. R of x here is this changing radius. So if we had just a quarter circle, it's these different, given an x value, it's the height at that x value. This is r of x1 maybe. If we have a different one, this is r of x2, right? So we have these different radii. What are they? All right. Well, what we can do is we can notice the radii here, they only matter in this xy cross section. So let's just graph that circle and see where we can get to. And it only matters for the top quarter also. So here we have x, here we have y. Let's graph ourselves a quarter circle. All right, great. Here's the quarter circle. And remember, we're looking for these different heights, essentially, these heights. All right, so what can we do? Well, let's say we've gone a distance of x out. Maybe we can call it, we're going a distance of x not out. All right, how far does that put us up? This is the question we're asking. How far does that make us go up? Well, there is the defining relationship of the circle is that x squared plus y squared equals r squared. So at all times, and this does come from the Pythagorean theorem also, at all times the distance is constant. It is r. This is also what defines a circle, is being equidistant at every point to the center. But this equation is also really useful because now we know an x, and r is known, so we can solve for the y. So we can say, if we just go ahead here, subtract x squared, y squared equals r squared minus x squared. We can take the square root. Y equals the plus or minus square root of r squared minus x squared. And the reason it's plus or minus here is because given a certain x, we could also go down and have the exact same continuation on the bottom of the circle. But we're not thinking about that right now, so we can not worry about that. We can get rid of this plus or minus, just call it the positive version only. And this is great. We have an expression for y. And remember, this y here, this y is r of x. Because if we're thinking about this y coordinate, if we pop back into 3D, we're drawing a circle around this. This is the radius of the circle with the area we're trying to calculate. So I'll get rid of it now because it's cluttering up the graph. But this y coordinate here, given the x, that is the radius we care about. All right, well, if we go ahead and plug it in, what do we get to? So we can take pi out, it's a constant, and go back to our integral here from 0 to r of, well, r of x is the square root of r squared minus x squared, because we're squaring the radius. And then this is just dx. So what does this equal? Well, what's really nice about the area of the circle is that we're squaring the radius, which is itself a square root. So the square root just goes away. We have the integral from 0 to r of r squared minus x squared dx. This is great. This is pretty simple, actually. So we have pi, and then so we can go into blue color. Again, I forgot to keep the pi blue, so I'll make up for it for you by making this blue. What is the integral of r squared dx? Well, it's x r squared, right? Just adding an x there, multiplying. And then here, we're subtracting. What's the integral of x squared dx? X cubed over 3. This is all from 0 to r. I'm going to scroll down here so that we have more space to work with. And what is this? Well, this is just pi. And then if we plug in 0, we have an x in both of these, so we know that the 0 term won't matter. So let's just plug in the r. We're going to have r times r squared minus r cubed over 3. And then again, the 0 term doesn't matter because we're going to just multiply everything in here by 0. It's going to all go to 0. So what do we get? Well, this is going to equal, get back to the yellow, pi times, and then this is just r cubed minus r cubed over 3. And something minus a third of something, that's just going to equal 2/3 of that something. So in the end, this is pi times 2/3 of r cubed. And if we remember what this is equaling, this is, if we just copy this part, this is, okay, I'll put the 1/2 v back there. We'll get another one. This is all equaling 1/2 of the volume. This is 1/2 of the sphere that we calculated. If you remember, we're going from 0 to r. We're summing up all of these circles, going from big circles to slightly smaller circles to nearly non-existent circles at the very tip at r. We're summing all of those circles up, and we're getting that half the volume equals 2/3 pi r cubed. So naturally, we can multiply both sides by 2, and we can get ourselves the volume of the entire sphere is 4/3 pi r cubed. This is pretty cool. That wasn't too hard. It was good exercise, and we just proved the volume of a sphere. And it seemed like a kind of hard thing to do, but we have it now. And if you remember from the area and circumference of a circle video, the circumference of a circle is also the derivative of the area. The circumference is the derivative of the area, which, 2 pi r and pi r cubed, or not pi r cubed, but pi r squared, sorry. This is indeed the derivative, right? And if we want to remember why that is, it's because if you add on a little bit of area here around the circle, if the width of that area is, if the width of that new ring is going down to 0, which is what happens as you do calculus, then that new bit of area is just going to be the border of the circle already, which is the circumference. The same exact thing applies for spheres, which is to say that the surface area of a sphere is equal to the derivative of its volume. And we know the volume, so we should be able to find the surface area. And indeed, if we go ahead and find ourselves what is the derivative of our volume, what do we find? R cubed goes to r squared, multiply by 3, 4 pi r squared. Hopefully it makes sense to you now why, or at least how, the formulas for the surface area and the volume of the sphere work, why they came about, how you can get to them. So there it is.